Assalamu alaikum everyone, welcome to the course of real-time embedded system. Today we are going to continue our chapter program design and analysis from the book of Van Wolf. Today is our lecture number 23 and we will continue from our previous topic of control data flow graphs. So let's start it. So as I've told you previously that in data flow graph we just have variables, we have assignments, we do not have any decisions, whereas in control data flow graph we have both control and data. We use data flow graph as components of CDFG. There are two types of nodes, one is decision node and one is data flow nodes. We have already seen the data flow node. Okay, so let's have a look at the diagram of this. So data flow nodes basically encapsulate data flow graph. So you can see that we have x is equal to a plus b and y is equal to c plus d. So what we are going to do, we are going to encapsulate this data. Okay, so data flow node will encapsulate the data flow graphs. Write operation in basic block form for simplicity. As we have seen that we have basic block forms. So basically we are going to use this data flow for our control flow. So on our certain control we will execute this data flow. So let's move on. So usually we have two forms of control. One is, you can see on your left side, is basically if statement. This one, either this will be true or this will be false. Depending upon this control we will evaluate our basic block, which is our data flow graph, which we are going to encapsulate. So this value here represents v1, v2, v3, v4. It's kind of a switch statement. Either we can go to v1, we can go to v2, v3 and v4. So these are the equivalent forms of control. So let's move on to next slide and have a overall picture of this control data flow graph. So this is the basic control data flow graph along with the C code. So we can go through the C code, and along with it we can have a look at the CDFG diagram. So if condition 1, it means that if condition 1 is true, execute this block bb1. So if condition 1 is true, we are going to execute this block. This is our basic block in which we have data flow graph. Okay, else if it is false, execute this bb2. So what happens if we have like true bb1? What we are going to do, if we have bb1 true, we will go to bb3. Okay, otherwise if we have false, from either way we are going to go to bb3. Once we reach bb3, you see in the code we have switch statement on c1, c2, c3. So we have three cases, c1, c2. If case 1 is true, it means c1 is 2, c2 it means, and if third case is true, it means c3. So in case 1 we are going to execute this basic block bb4, and in case 2 we are going to execute this basic block 5, and finally basic block 6. So this is how our CDFG looks like. Okay, so a CDFG uses a basic data flow graph as an element. So here we have data flow graph as an element, adding construct to describe control. And what we are doing, we are using construct to it. So these are elements, and what we are using construct to describe the control. In basic CDFG, we have two types of nodes. I have told you, decision nodes and data flow nodes. So you can see these are data flow nodes that are in square, and decision nodes are in diamond shape. A data flow node encapsulates a complete data flow graph. So why we are saying encapsulating? Because this data flow nodes have all the things that we have stated previously that we discussed in data flow graph. We can use one type of decision node to describe all the types of control in a sequential program. For example, jump, branch, is after all the way we implement all those high level control constraints. So here we have explained how this CDFG works. These are our two nodes, the data flow node and the CN node. So I hope this is pretty much clear. Let's move on to the next slide. So again in this slide we have a description of control data flow graph. So we have some data. Where we have data? Here we have some data. Here we have some data. So these are encapsulated data flow graph. This is encapsulated data flow graph. Here we are doing decision, so that is our decision node. So initially I is equal to 0 if I is less than n. So this, what we are going to do, we are going to execute the body of the loop, and once it is done, just go back and check the statement again whether I is less than n or not. Same thing goes for while or for loop. We can use this CDFG. So let's move on to the next slide. So in this slide we are going to talk about assembly and linking process. So program generation for compiling through loading. So this is where you write code in your high level language, then it goes to compiler. Compiler transforms this code into assembly code, which is human readable instructions, and then these human readable instructions are transformed into bit level instruction with the help of assemblers. And one thing that assembler do, it does translate the labels into addresses. So it translates the labels into addresses and also take care of the format of the instruction. So most of the time we do not make a compiler that generates directly the machine code, that executable binary. Rather it makes a assembly code. Why? Because it frees the compiler to know the address of the instruction in memory. Also it frees the compiler to know the exact format of the machine level instruction. So all this process is often hidden from us by the compilation command. So we do not know like what is assembly code, assembler, object code, linker. All this is hidden from us, and this all is done by the compiler. Now the assembler job is to translate symbolic assembly. The assembler job is to translate symbolic assembly language statement into bit level instruction. So it is a bit level representation of instruction known as object code. So assembler basically transforms the assembly language statement into bit level representation of instruction known as object code. The assembler takes care of instruction format and translate label into addresses. However, the program may be built into many files. The final step is determining the address of instruction, and data are performed by linker. So what does linker do? Because we can have main program in many different files. So the purpose of linker is to like combine all these files, okay, and determine the address of the instruction. So all the addresses of the labels are determined by the linker, and which produce executable binary file. And the purpose of loader is to bring the program into memory for executable purposes. Okay, so loader basically brings the program into memory. We know that the executable binary file could be somewhere else other than the memory. So the purpose of loader is to bring that file onto the memory so that we can execute it. So that was about this assembly and linking process. So everybody needs to know what does linker do and what is our object code here. So these are the important things that one must need to know. One thing more about linker allows a program to be stitched together. So what we do, we have different files, so we have different labels, we have different addresses. So what does linker do? It allows a program to be stitched together out of several smaller pieces. Okay, so that was about this assembly and linking. Let's move on to next slide. So in this slide we are going to talk about multiple module program. For example, a program is composed of several files. So if it is composed of several files, it will have several modules. We can call it multiple modules. So in that type of program addressing become more specific during processes. So during processing we have two types of addresses. Number one is absolute addresses. Absolute addresses are measured relative to the start of the CPU address. So it will remain fixed start of the CPU address, or it is provided by the programmer. Relative addresses are measured relative to the start of the module. So in one case we are measuring the addresses relative to the start of the address space CPU, and in other we are measuring with respect to the start of the module. So if we have main program, then we have another module. So what we are going to do, this will be the module will be the relative address. Okay, so these are our two types of address: relative address and absolute address. So let's move on to next slide. In this slide we are going to talk about the major task of the assemblers. So assembler basically generate binary code for symbolic instruction. So compiler basically transform the high level instruction into symbols, and then assembler transform these symbols into binary code. Also it translates label into addresses. So the labels that we are using in assembly code for jump purposes or for control flow purposes, they are basically translate into addresses. Assembler handles pseudocodes. So for pseudocode we usually don't generate any instruction. Assembler allows label to be added to the symbol table. So we add symbol to the symbol table without occupying the space in the program memory. So once we are not specifying the space in the program memory, it is known as pseudo-ops. So no instruction generated. So generally the task is one-to-one translation. So for one symbol we are going to generate binary, for one label we are going to generate address. So this is one-to-one translation. So in this slide we are going to talk about symbol table generation. So before I talk about symbol table generation, we need to understand the labeling process required two passes through assembly source code. The first pass scans the code to determine the address of each label. The second pass assembles the instruction using the label values compared in the first pass. So these two passes are kind of related to labeling of the addresses. So we use program location counter to determine the address of each location. So if we have a program, so we are using PLC to determine the location of to determine the address of each location. We scan program and keep track of the PLC, keep counting of PLC, and we do it in the first pass, and we generate addresses during the assembly time, not execution time. Okay, so this is about the assembly table. We are going to look at the symbol generation table in next few slides. So in this slide we will talk about symbol table. So on the left side you can see that we have assembly code, and the assembly code is initialized with the origin, that is 100. So this code will start from the memory location 100, and this value will be loaded into the program location counter, and this will be the starting origin of the code. So you can see that we are assigning in symbol table we have labels and we have the addresses of the label. For example, the first one, label 1, is at 100 location. Then these two statements required kind of 8 locations in memory. So label 2 will start at 108, and then again these two requires 8 spaces in the memory. So we will have 16. So this is for immediate addressing. This is like LDR, and these statements are basically the statements that we execute on ARM microcontroller, so advanced RISC machine, and BLE basically the branch less than equal to. So these statements, these assembly language code is in accordance with the ARM processors. So anyways, we need to know how we create this symbol table and what is there. So this is what we have in symbol table. We have the addresses, and we have the starting address specified this org, which is basically origin of PLC. Let's move on to next slide and explore something more. So linker is basically a two-pass assembly process. In first pass, we generate symbol table as we have shown you. In the second pass, we generate binary instruction while using label values from the first pass. So we use label values to generate the binary instruction in the second pass. So pass 1 is basically the symbol table generation, and pass 2 is basically the binary instruction generation. So as I've already talked to you about the pseudo operation that do not generate instruction, mean that they are not required in memory location in the memory. org sets program location, as I've told you that org basically tells us about the origin, and EKU generates symbol table entry, okay, and data statement define data blocks, as we have already seen in the data flow graph that data statement define data blocks. So that was about the pseudo operations. Let's move on to next slide. So in this slide we will talk about relative addresses and external labels. As I've already told you that we have two types of addressing. One is absolute, in which address is measured reference to the CPU address, or we specify address, and in that type of address we do not have different modules, so our control is not transferring from one point to another point. Whereas if we have various files, we will have modules. In that particular case, the address will be measured relative to the module. Labels within the module may be kept in relative forms. So you will need to keep the labels in the module in relative form. And we are not sure that we will be able to get access to all the label values at the assembly time. And we must need to keep track of external label. We cannot generate full instruction that use external labels. Okay, can't generate full binary for instruction that use external label. So we must need to keep track of the external labels. I'm going to explain this with the help of example in next slide. And as I've told you, linking is basically the solution of stitching all the modules together. So combine several object modules into a single executable module. And what is the job of linking? Put modules in order. So as I've told you that we do not know about all the addresses, all the labels during assembly time, because we do not know about the order of the module. So what does linker do? It puts the modules in order and resolve label across modules so that we can have complete labels across all the modules. So basically linking is the work in which we stitch all the smaller pieces of programs into one executable module. So in this slide we are going to talk about the external and entry points. So this is one separate file. We can say this is one module, this is second module, and these are labels. So this triple X and triple Y are our entry points that are defined in the same file. Whereas for this file, A is the entry point, A is the entry point. And if you see here, this A for this file is the external reference. And likewise for this file, triple Y is the external reference. So external reference is used in this file but is defined somewhere else. So let's take a look. This is entry point, this is external reference. Okay, so for this file this is external reference, for this file this is entry point, and these two are again similarly, this is your entry point, this YY, and this is external reference. So in this slide we are going to talk about the module ordering. We have talked about that program can consist of different modules, and on the basis of different modules we have different addressing modes. We have relative addressing, we have absolute addressing. In module ordering, core modules must be placed in absolute position in memory space. We use load map or linker flags to control the order of the module. Modules and files are the similar thing. These are just the small portion of a big program. So for example, a program can consist of 10 modules. So we can say that a program has 10 files. The linker is a two-phase process. First, it determines the address of the start of each object file. The order in which object files are to be loaded is given by the user, either by specifying parameter when the loader is run or by creating a load map file that gives the order in which files are to be placed in memory and the length of each object file. It is easy to compute the starting address of each file. At the start of the second phase, loader merges all the symbols from object into a single large table. Now, controlling where code modules are loaded into memory is important. For example, you can see here we have module 1, module 2, module 3. We have ordered it, and where we need to store it in the memory is important in embedded system. Some data structure and instructions such as those used in manage interrupt must be put into specific memory location for work. So for example, if we are working with the interrupts, so we need to put that part in some specific location in the memory. So that was it about the today's lecture. We talked about modules, we talked about addresses, we talked about linker, we talked about loader, and we started with the controller data flow graphs. So I hope that the things are entry point, the external reference, all are clear to you. Thank you very much.